In this video, we are going to give an introduction to estimation chapter by looking at several definitions and notations. One of our main goals in this chapter is going to be an estimate some unknown parameters in population. Let's assume that you are trying to estimate average height of Kazakhstani population. So we have a general population with some unknown parameters, let's say mu, mean, and variance. So we'll try to estimate those two parameters in this chapter. So our first logical step would be to draw a sample. Let's say a sample of size n out of our general population. Then we are going to measure, so our sample size is n here. Then we are going to measure a height of every person in our sample. So from now on, we'll be referring to uppercase letter x's as to random variables. So every x from x1 to xn is a random variable that is drawn from our general population here. And the single realization of these random variables will denote in small letter x's. So uppercase xi's here are random variables. From our general population, and lowercase xi's are just numbers. So these are just numbers like, let's say 1.7 meters, 1.9 meters, and so on. Now, these n random variables, our sample here, we call these random variables as IID. This is short for independent. So we assume that our draws from general population here are independent. In practice, this is not very easy to obtain since we have some other factors involved like sampling bias and some other complications, but we'll assume that these are independent. Identically, second I is for identically distributed. So we assume that these random variables are from the same distribution, which follows our general population here. Let's assume that PDF of general population here is given by some bimodal PDF here. So this is PDF for height in our general population there. All right, then what is our next step? Our next step would be to measure sample statistics here. So we are going to measure our basic logical guess would be to measure X bar. So X bar here is an average of these random variables. And this is a random variable itself. Then an average of this size is small X bar. So this here is a single realization of uppercase X bar, which is a random variable. So this is just a number, whereas X bar is a random variable. Now let's go over some of the definitions. So the sampling distribution of X bar is the distribution of values of X bar over all possible samples of size n that could have been selected from the reference population. Now, sampling distribution of X bar. So we said that X bar is a random variable. So X bar itself is going to have some distribution. Now, numerical summary of a sample is called a statistic. The sample mean X bar and the sample variance a small s squared are examples of statistic. Here, sample statistic is X bar, and if we measure its variance, it is denoted by smaller case s squared. Numerical summary of a population is called a parameter. Population mean and population variance, sigma squared, are examples of parameters. So we use Greek letters to denote the parameters from our population. So this is statistics from our general population here. So we use statistics to estimate parameters. So we use commonly we are going to use X bar and X squared. So these are statistics from our sample to measure parameters in general population. Now, if we are going to use X bar, which is our sample mean, to measure parameter of general population mean. This X bar here is going to be our estimator. Estimator for population parameter mu, for population mean. This is our parameter. Now, as we said, our first logical guess would be to estimate population mean using X bar. So in that case, estimator is X bar, and the parameter that we are trying to estimate is mu. Now, our second question is how good is that estimator? What would happen if we simply used, let's say, one of those single random variables as an estimator for a general population? Now, first definition that we are going to introduce is a bias. Bias of an estimator. Bias of an estimator is equal to expected value of our estimator, theta bar, minus the true value of population parameter. So for estimators, we are going to denote our estimators as theta bar, and population parameter is denoted as theta here. Now, theta bar, this parameter is unknown. However, this is not a random variable. The value of it is somewhere out there. So this is just a number. And if we would take an expected value of theta of a parameter, it would simply be equal to theta. It's like taking an expected value of a constant. So we'll use this fact a little bit later on. All right, now what does this expression here imply? So first, a measure of how good estimator is bias. So we want, on average, the value of our estimator to be equal to the true value of population. And in that case, we'll call that an estimator as unbiased one. So unbiased estimator is the one with the bias equal to 0. So in other words, we want on average its value to be equal to the true value of population parameter, which means that we want its bias to be equal to 0. Now, let's try to measure. So in that case, our estimator theta bar is x bar, and our parameter is population mean mu. Let's try to measure a bias of that estimator, a bias in the case when estimator is sample mean. So bias of x bar is then equal to expected value of x bar minus the value of theta true population mean minus mu. So this is an expected value of sum over all xi's over n minus mu. So I is running from 1 to n. Then we know that expected value is a linear operator. I can factor out 1 over n. Then I will have the sum from running from 1 to n of expected value of xi's minus mu. Now this value here is equal to mu. Since those xi's are simply random variables that follow the density function of our population. Then we have the following expression, 1 over n, the sum from I to n of mu's minus mu, which is equal to 0. So, which means that this is good. So our estimator x bar is, if we look only at the criteria of bias, then this is a great estimator since it's unbiased. So x bar is an unbiased estimator. Of population parameter mu. All right. Then our next question, is that enough to measure how good our estimator is? Well, it turns out that it is not enough since we have other, we can come up with other estimators that are going to have exactly the same bias of 0. So let's assume that first we are going to sample a sample of size n from our general population. So we'll have n random variable xi's here. Let's assume that we are simply going to select one of these values here in our sample and use it as an estimator for mu. So in other words, we are going to get a sample. Then we are going to randomly select one such random variable from our sample and use it to estimate population mean mu. Let's try to measure a bias of that estimator. Well, it turns out that the bias of that estimator is also going to be equal to 0. So bias of xi is then equal to expected value of xi minus mu, and xi is simply a random variable drawn from our sampling from our population density here. We'll have a mean mu minus mu, which is 0. So simply taking a single random variable from our sample here and using it as an estimator, it turns out that this estimator here is also an unbiased estimator for population mean. We can also, let's try to come up with one more estimator. Let's assume that we are going to line them up in an increasing order, and then we are going to select the smallest and largest value in our sample. So it turns out that this estimator is also going to be an unbiased one. So we are going to need another measure for goodness, for the quality of our estimator. Right, let's come back to our lecture slides here. So, here's a nice plot here, which shows as a bias of estimator. So it seems like in the first graph here, a bias of estimator is equal to 0, since the true value of population parameter is lining up perfectly with the mean of our estimator theta 1. Now, in that case, this estimator here is biased, since the value of true population parameter is not lining up, is not equal to the mean of our estimator theta 2 hat. Now, let's take a look at the following plot. So here we have three estimators. First estimator is X bar, second estimator is median, and the last one here is an average of largest and smallest observations in our sample. What we did here is we have drawn 200 random samples of size 10. Then we made a histogram for each estimator, and these histograms here are going to give us resemblance with PDF of each estimator. So here we can say that this is a PDF of X bar, this is a PDF of median, and this is a PDF of largest and smallest observations in our sample. Oh, so this is mean of xi over 2. All right, now we said that we want first our first criteria we are looking for is that we want our estimator to be unbiased, and the second logical guess would be is to make our estimator as stable as possible. So we want consistent results from our estimator, meaning that we do not want to values that are given from our estimator to be too much varied. So second criteria that we have to look at is that variance of our estimator. So here we can see that those two plots of PDF of X bar and median are more or less compact if we compare it with a PDF of an estimator which is average of smallest and largest observations in our sample. Second criteria we'll be looking for is variance of our estimator. Meaning that we want a variance of our estimator to be as small as possible. Now, ultimately, we have to look at both bias and variance of our estimator to measure how good our estimator is. And this is done using mean squared error. So mean squared error is an ultimate criteria to measure the goodness of our estimator, which is equal to bias squared plus the variance of our estimator, and is given as expected value of our estimator minus the true value of parameter squared plus variance of an estimator. This is also equal to a simply expected value of theta hat minus theta squared. So we want this value to be as small as possible, and the best estimator is the one with the minimal value of mean squared error. Now, first, let's show that this equivalence here is true. So, expected value of theta hat minus theta squared is equal to, let's open up brackets here, theta hat squared minus 2 theta theta hat plus theta squared. Expected value is a linear operator, so this is expected value of theta hat minus 2 theta theta hat. Now I factored out 2 theta here as a constant since previously we said that even though the true value of population parameter is unknown, it is somewhere out there. This is not a random variable, it's just some number. So we can consider it as a constant in that case, plus expected value of theta squared, which is simply theta squared. Now, this is equal to, let's try to bring that in the form we have here. This is equal to expected value of theta hat squared minus expected value of theta squared. So I'm going to artificially add this term here, plus expected value of theta squared. Oh, this is all expected value of theta hat. So this expression here is then the variance of theta hat minus 2 theta expected value of theta hat plus theta squared. So this is going to be equal to variance of theta hat, so sigma squared of theta hat, plus this expression here can be grouped up in the following square brackets, expected value of theta hat minus theta squared. So we obtain the same expression that is here.